Similarly, we have got the public distribution system where the food is given to the families in restricted quantity so that everybody can get food. Similarly, in a computer system also, we have got a number of resources. What are these resources in a computer system? The resources, I'm sure it has been discussed at the beginning. We have got memory, and Professor Animesh Datta is talking about memory management. So memory is one of the resources. Um, we have got limited number of I/O devices. We have got limited amount of memory, limited amount of I/O devices. What else? What else resource do we have? Anybody? The disk space is limited. We don't have infinite disk space. Whatever GB or terabytes we have, but still that's a finite limit to that. So we have got, similarly, we do not have infinite number of printers connected to our system. We do not have infinite number of input or output devices connected to the system, right? So we have got a limitation of the resources. The number of resources are limited. Now, who are the consumers? In the analogy that I gave, the consumers were the human beings, right? That's why we're requiring public distribution system and everything. Now, who are the consumers in our case? It is said that the consumers are processes. Now, I am making two basic assumptions in this lecture. One is that all of you are familiar with the architecture of the computer system. Can I assume that? Chiranjit, can I assume that?
Yes, sir.
Yeah. So all of you know that computer consists of CPU, memory, I/O, short-term and long-term memory, the ROM, RAM, and the hard disk, and even much faster caches and everything. And since there is a limited number of resources, limited amount of resources, that's why Professor Animesh Datta is teaching you memory management, since the memory is limited. Now, the consumer being the processes, what is a process? Let us say when a program is written, what is a program? A program, all of you know, is a piece of code. And when a program is written, where is that program stored? Anybody? Riddhi Roy?
Yes, sir.
Riddhi? Riddhi, I can't hear you.
Yes, sir.
Where is the program stored when a program is written and saved?
In the secondary memory. When it is saved.
Absolutely. Pardon?
When it is saved, it is stored in the secondary memory.
Absolutely brilliant. It is saved in the secondary memory. So I'm trying to, I'm just trying. This is my first attempt. I want to share my screen. Just a minute.
Sir, you can present your screen. There is an option of presenting your screen.
I know. I'm trying with that. Just wait a second.
Okay, sir.
স্যার প্রেজেন্ট নাও বলে একটা আছে ওইখানে ওটা ক্লিক করুন
আমি জানি বাবা আমি আমি যে স্ক্রিনটা শেয়ার করতে চাইছি সেইটা আসছে না কেন? Wait a second. Is a white screen shared with you? No?
It was
It
shared, sir. It
was.
just went off.
White screen was shared.
Yes,
It
sir.
got shared, but it went off immediately.
Okay, just a minute.
It just
Now?
came. Yes, it
Yes, sir.
came
Okay, okay.
there.
All right. So, just tell me whether you can see what I'm writing here. Uh, Time is wasted because of this. Yeah, so we have got the programs, right? So something, I'll need some time, just a minute. Why is this not writing now? I succeeded in writing on this, but I don't know why it's not writing now. Uh, I don't know why.
Sir, I think you have to select the pen. Then only you can write.
No, all those things are there. I've got selected. It's somehow. Okay, let me continue a little bit and then I'll see again. Just a second. So I'm stopped sharing for the time being. I'll try after a little bit again. So essentially, there is a difference between a program and a process. It is said that a process, I said that the process is the main consumer of all your resources, right? So a process is a program in execution. It is said that a process is a program in execution. Now, when I say it is a program in execution, what is the great thing that I am saying? A program and a program in execution. A program, therefore, is a static entity that is remaining inside the hard disk and is not being able to create much change, right? And anything that is in execution is an active entity. And any active entity creates a change, brings in a change in the environment around you. Now, when we say that a program is executing and it is a process, what are the changes that it is bringing in? Can anyone tell me? Can anyone tell me what are the changes that a program, when it executes, brings in? Akash Manna, Muhammad Umar, all of them have left the class or what? Devaditya Datta,
Yes, sir.
yeah. So at least you are there. So can you please tell me what actually changes when a program is executing?
Sir, when a programming is executing, it is transferred from the secondary memory to the primary memory to be executed.
Yes, that is required. That is required. I think the student just now earlier said that when I save a program, it remains in the secondary memory. And when it executes, obviously, it has to be brought to the primary memory. Now, the first question is who brings it to the primary memory and what is meant by bringing it to the primary memory. We'll come to that later. But that has come to the primary memory and now it is executing. As it is executing, what is changing actually? As it is executing, what is changing? Yes, Devaditya, you can continue.
Yes, sir.
Tell me, what is changing? Anybody? Anybody? No. So, see, when a program executes, it is changing many things. First of all, it is changing the status of the variables. Suppose in a program there are 3 variables A, B, and C. And the program code is just C assigned A plus B. So A and B were 2 and 3, and C's value was obviously unknown in the memory. When the program is executed, now we have got A to be 2, B to be 3, and C to be 5. So from A, B unknown, we come to A, B, 5. So that is a change of status of the variables, right? Similarly, we have got other things changing, like for the program counter is, after every execution, the program counter is changing, right? The program counter is increasing, and therefore the program counter is also changing. The memory capacity, the memory is also changing, because the when the program was in the secondary memory and was not being executed, that means it was not a process, it was in the secondary memory, and some part of the primary memory was free. So that part is now being consumed by the program that is being executed. So the status of the program has also changed. So there are a number of things in the environment. If I call all these things as environment, then the environment changes with the execution of the program, right? So that is why we call that a process. It is a process because it is changing the program. It is causing a program to be executed, right? So that is the first point you have to understand. Let me try once again. My tablet is working now, so let me just try to share once again, if I may. What is happening again? Yeah. So we now know that there is something called process and there was something called program. And also we know that a program is converted to a process, and at that time the process is actually changing the state of variables, right? Changing the state. And since the state is being changed, this is called the process. Okay? Now, since it is, and this is also a dynamic entity, it's no longer a static entity. And so the resources, now here if I look at this to be my memory, and in my memory I had some part of the RAM, for example, these parts were already consumed by some other processes. Say this part was consumed by, and when this new program became a process, then another part of the memory has been populated by that particular program. Now, so this picture of the memory has also changed. Now, as the process I've just now said is a dynamic entity, it goes through a number of states. And let us see what these states are. We can simply draw a thing called a process state diagram. Where this looks something like this. You can note down also that when the new process starts, we start with new. So this process, when it is new, where is it? Anybody, I invite you to answer. Please be interactive. Let's see how much interactive we can be with this new technology. When the process is born, where is it? It is in the secondary memory. It's a program. Now, it will be executed. So where will it be? As you had said, it will be in the primary memory. So from here, there is a transition and it comes to the primary memory. And that is a new state called the ready state. Briefly I write it RDY, ready state. So here it is in the secondary memory. Here it is in the primary memory or the cache. And then when you just give the command ./a.out or you give ./myproc.c, myproc.out, all right, myproc.exe. At that time, what happens? The program, which is in the primary memory, starts getting executed, right? And so this will go from the ready state to the execution state. All right. So it is executing, and from execution, what can happen? It completes satisfactorily and goes to the terminate state. So it's finished or terminate. The program is over. As the program is over, that is no longer a process. It ends there. Am I clear? I want to hear yes or no.
Yes, sir.
Yes, sir.
Louder, louder.
Yes, sir.
Yeah.
Yes, sir.
Thank you.
Yes, sir.
Thank you.
Yes, sir.
Okay, thank you very much. So it comes to the finished state. That is all very nice, very fine, as long as things are progressing in a very beautiful manner. But unfortunately, we also have a scarcity of resources. Now, when this program that was running in execute, encounters an input-output statement. Suppose it wants to print a file or print some data. That will take some time, isn't it? Now that input-output will be executed. When a file is printed, who prints that? The printer. And the printer is not as fast as the CPU. So it will be slow. So naturally we think, why should we block the CPU for so long? Instead, let's make the CPU free and let the printer do the work. So when from execute, I have got some IO tasks coming in, input output, then I go to another state. Now this is a very confusing English. I'm saying you should be careful about it. I am saying I, who am I? This I, this is, you must be very careful about it. A program was executing. Let me tell in passive voice. A program was executing. The program encountered an input or output operation. So the program has gone to another state. And that state I can call a wait state or IO state. or IO state. So it remains there. And why it is doing this in this wait state, I'll show you, tell you later that, and remind me if I miss it, that not even IO, it can also be in the wait state for some other reasons. But let's take the simplest case, the IO, it is in the wait state. So here it is doing some IO. And while this process is doing its input output, for example, printf, so and so, so and so. So that thing is being done here. Another process, which was in the secondary memory, or which was in the primary memory, the diagram that I had drawn just a couple of minutes back, that process can come to the CPU. So here it is in the CPU, right? It was in the primary memory and it is in the CPU. And since the particular process which was here, this red process, is now in the IO, so this, where is the eraser? I hope this is the eraser. So can I erase this? Yes. Oh my God, this has also got erased. So let me put this. And here, another blue process comes up. While the red process is doing this IO, the blue process gets the CPU and is executing. And is executing. It has not completed. Neither it has come to the finish. All right, neither it has come to finish. So, it has not come to finish, but the IO has been completed here. As the IO has been completed here, this process, red process, need not be in the wait state anymore. It comes back to where? Right now, at that point, the CPU is not free. In the CPU, this blue process is running. So this red process is actually again coming back to this ready queue. And it is off from here. It is off from here. And it has come back to the ready queue. Therefore, I had another link that from this wait state, what's happening? From this wait state, it can go back to the ready state. So right now, what is the scenario? One process, the process which was in the CPU few moments back, has made a transition to the wait state and has now gone back to the ready state. And another process is executing in the CPU, the blue process. Now, there are so many processes. Let me put another green process inside the ready queue. All right. And let me put another black process inside the ready queue. In this ready state, sorry, ready queue, don't take that word for the time being. In the ready state. In the ready state means where? I want an answer from you. Our process is in ready state means where is it residing?
Primary memory.
The primary memory.
Fantastic. It is in the primary memory. So right now in the primary memory, I have got a red, green, and black. And where is the blue? Inside the CPU. Now this blue process is a very long process and is taking a lot of time. And this black and green and red are shorter processes which are waiting in the ready queue. And waiting in a queue. Again, let me not delay it further. Since these are process state diagram, all of you are bright people, so you will understand that when we say that the processes are waiting in the ready queue, ready state, they are actually in a data structure that is known as the ready queue. All right. So in this ready queue, suppose this red process was in the wait when the green came. So the green is here. Then the black came. The black is here. And then from wait, this person came. So this red is here. So this is the form of a queue. All of you remember queue from your data structure class, right? Right or wrong?
Yes.
Yes, sir.
Yeah.
Yes, sir.
It is a first in, first out, right? So the green is there. Now this person is taking a lot of time and I cannot allow him to go on and on and on. So therefore, but these people in the ready queue, that means in the ready state, are waiting. So the operating system will have to do something. Suppose somebody is there and has taken up the ticket counter, and is waiting. Purchasing tickets for 50 people, and then the people who are standing at the back start shouting, "Arey bhai, ek baar aiye," etc. So he will have to go. So he is forced out from this execution state to the ready state when there is a timeout signal. Timeout. Now this is a very important concept. Timeout. Time over. So this blue will have to leave the CPU and will have to come back to the ready queue. That means what? In the ready queue, which I was drawing, now there is another person, the blue, who has come here, and consequently the blue is gone from here. So now this is the state. Agreed? Yes or no?
Yes, sir.
Now
Yes,
the
sir.
operating system will decide who will get the chance to run in the CPU. Now typically in a queue, where is the first in, first out? Who in your judgment should get it?
Green.
Green. So the red, why? No,
No,
green.
sir, green.
Green. So the green comes here, and green is out of this ready queue. And who is there in the ready queue? Now who is leading the ready queue? The black is leading the ready queue. So this is a scenario that has changed. And this will be going on. And suppose the green is a nice little fellow. He has finished execution and he completes. So it goes to the finished state. You are happy with the result. Now again the CPU is free. As the CPU is free, the operating system will wake up and will schedule the next process. Who is the next process?
Black.
Who is the next process?
Black one.
Black one. So the black one will come here and start executing. And I'm just revising now. And so this will be gone. Right. So now again, the black one needs an IO, has encountered a print operation or something. Where should the black one go? Which state?
Wait state.
Wait state. And so similarly, just because as we had ready state, I have also a wait queue here. That's another data structure that we need for operating system design, right? Wait queue. So in that wait queue, the black comes here. That means the black is here, and the black is gone from here. And so who takes the place? Where's the black? The black is gone. Now who will take the place? The red will be in execution, and the red is out of here. Now when the black finishes the IO and the red is executing, what will happen? Where will the black go?
Ready state.
Black will again go to the ready state. So the black will go here to this path, and this will be over. Fine. So in this process, it will go on, right? So a process will relinquish, note this very carefully, it will relinquish the control of the CPU. It will be in the CPU or not be in the CPU, right? In Hamlet, there was a fantastic statement, to be or not to be, that is the question. So here, whether it will be in the CPU or will not be in the CPU will be dependent on whether it is doing some execution, number one, or whether it will not be in the CPU if it needs an IO, or or
If it takes more time.
if it takes more time, if it is timeout, or it finishes, right? So if it takes more time, now we'll conclude today's class with this part, timeout. Now, who is doing this? All these things, time we are saying somebody is doing this, somebody is doing that. Who is doing this? Operating system is doing this. Now, there is a $1 million question here, which we'll take up in the next class also. What is an operating system, a hardware or software? Hello?
Software.
It's a software.
Software.
Yes. And the software, can it run by itself? All of a sudden, the software on your paper is running. Can it happen?
No, sir.
It requires the processor, right? A software cannot run without a processor. Therefore, whenever we are taking some decision and making these transitions happen, this is being done by the operating system, which must come inside the CPU part and will execute. We'll come to the detail of this in the next class. But remember, let's conclude today with this timeout. Okay, this timeout. How did something was running? This red process was running here. How did we come to know that time is out? And who is deciding on the time? So, Shubrata, please note down this. I'll try to answer these questions in the next class, but because we'll have 40 minutes class. But for today, just remember, tell me before the class that how do we know that the time is over, etc., etc. But we need, say, and how much time is required and all those things. We'll talk about that, the different type of processing. But right now, let us conclude with this point. We have got 3 minutes. Rate process was running here. Fine. Now the operating system pushes it back to the ready queue because it is timeout. How do we know that it is timeout? How do you know that it is timeout? I hope you remember this term, interrupt. Are you familiar with this term? All of
Yes,
you?
sir.
All of you?
Yes, sir.
Anybody know? All of you know interrupt, right?
Yes, sir.
Yes or no? Yes. So, although operating system is a software, we need the help of some hardware. And the hardware whose help we need is a timer. A timer is a hardware circuit. Very simply speaking, in old days, 555 timer was there. Now in any processor, Intel, you will find 8252 chip, which is a timer. So that is there inside the computer system. And when a program is loaded inside the CPU, suppose this is a timer. This is a timer. As the process is loaded in the CPU by the operating system also loads this timer with some time value, say 5 milliseconds. That's a very typical time. And as the program starts executing here, this timer starts ticking down. Tick, 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 it ticks down. So it becomes 5, 4, 3, 2, 1, 0. As soon as it is 0, this sends an interrupt to the CPU. And that informs the CPU that this interrupt has come. And all of you know that when an interrupt comes, which program runs?
It's a system interrupt.
Interrupt service routine.
Absolutely, the interrupt service routine. And this particular interrupt service routine for this particular timer will be nothing but the operating system module, which will take this one out, which was running and put it in the ready queue. All of you now know data structure. Put it in the ready queue, and what that it is, we'll discuss in the next class. It will put it in the ready queue. All right, and it will find out the next eligible system from this ready queue and put it in the CPU. That is how a process state cycles in a multi-programming and time sharing system. Okay. Next class, we'll start with time sharing, multi-programming, multi-processing, and all these things, and we'll come back to further details of the process. Any questions? Quick questions? No questions? Okay, you think about it today, and if there be any question, I'll deal with it in the next class. Okay, hopefully I'll be able to take the next class on Wednesday as well, unless I'm stuck with some other work. Okay, is it all right? The time is... Yeah, Subrato, now you please take over.
Yes, sir.
Okay, so I think the class was till 5:10, right?
Yes, its scheduled time is up to 5:10.
Yeah.
40 minutes each.
Let's stick to the scheduled time. So if no one has any question, if you have any question, you can please write it down, email me or to Subrato so that I get it before the next class. All right. I suggest that because I get too many mails, so if you have got questions, you please mail it to Subrato or Animesh, and they will collect it and give it to me before the next class.
Yes, you can. You all can mail us, and we will compile it and forward it to sir.
Okay. Thank you. Goodbye.
Thank you, sir.
Are the students still there or they have left?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Okay. You have understood. You have got what I said.
Yes, sir.
Okay.
Yes, sir.
So now the
Yes, sir.
Okay. Thank you. Thank you.
Okay, sir.
Thank you, sir.